Hello again. You are welcome to part 2 of the common emitter amplifier configuration. In part 1, we implemented the circuit without explanation, but in part 2 here, what we seek to do is implement the circuit and offer explanations as to the workings of the circuit. So if you don't mind, let's get into it. This is the circuit we implemented. So it is a two-stage common emitter amplifier biased by 22k here, biased by 220 kilo ohm here. This is 47, if you recall in video 1, 47 ohms, and this one was 1 kilo ohm. Very well. You notice that this is a PNP transistor. It is biased so that its collector is fed into the base of the NPN transistor here. So this is T1. In the video it was TRP42, and over here T2. In the video it was TRP41C. So TRP42, TRP41C. Now, since this is a PNP transistor, the voltage that will bias this transistor into conduction will be the RB1, the other at the top. If it were NPN, it would have been the resistor here. Okay, so let's look at the voltage on RB1. The voltage on RB1, this one is simply by ratio and proportion. So we have 22 over, this is 220. 220 plus 22, all by the supply voltage. If you do the math, you arrive at 1.09 volts, which approximates to 1.10 volts. So that will be the voltage on RB1. So voltage on resistor on base 1 is 1.10 volts. So what will be the voltage on RE1? The voltage on RE1 will be the voltage on this resistor minus the BEP drop, which behaves like a diode. The BEP junction of a transistor behaves like a diode, so it will lose 0.7 and the rest will come and collect on RE1. So voltage on RE1 is equal to voltage on RB1 minus 0.7, which gives us 0.4 volts. To guarantee the 0.4 volts on RB1, we have to make sure that RE1 is large enough. The ratio between RE1 and RB1 should be 100 to ensure that the voltage divider circuit is maintained. Otherwise, loading effect will occur. For instance, over here we have 47 ohms. I'm saying that if you multiply 47 ohm by beta, the value that we get should be at least 100 times the value of RB1. Otherwise, the loading effect will be so much that the voltage divider circuit you have established will be changed. Okay, so in your implementation, get a resistor large enough to ensure that the voltage divider circuit is stable. I have used 47 ohms because it is all I had at my disposal. Okay, now what will be the current that is passed by RE1? By Ohm's law, we know that voltage over resistance gives us current. So Ohm's law, we say current is equal to V over R, which means that our voltage 0.4 divided by the 47 ohm resistor that we have here should give us a value, I think 8.5 milliamperes. I think that should be right. 8.51 milliamperes. Let's say it is 8.5. So that would be the current that will be passed by RE1. Now, what is the collector current? We can take for granted the assumption that our base current is small. So small that it can be ignored. If so, then we can say that the emitter current, which is passed by RE1, is equal to the collector current. But if you seek more accuracy in your calculation, then we can do something like this. We know that emitter current is equal to base current plus collector current. We also know we can find the base current by dividing the collector current by the beta of the transistor. So the equation now becomes this. If you solve the equation, what you arrive at is this. We have the denominator being beta. So we have collector current here, right? Plus beta by collector current. If you simplify further, you arrive at the emitter current being equal to collector current, B plus 1, right? All over B, right? Which means that if you want to find the collector current, if you want to make the collector current the subject, it means that collector current, if you are given emitter current, will be equal to, so we have this one is emitter current. We invert this one, this will be B over B plus 1, right? So if you want more precision, use this to get the exact value of the collector current. But I want to rely on the assumption that our base current is so small, so collector current and emitter current are equal under this circumstance. So I'll not be deploying this maths. So going forward, our voltage on the collector resistor here, the 1 kilo ohm here, will be the current that has been passed here by this. Again, Ohm's law says V is equal to IR. I is 8.5 milliamperes. Our resistor is 1K. That approximates to 8.5 volts. That will be the voltage on the resistor on collector. The rule of thumb here is that in your bid to design this amplifier, the collector should sit midway voltage supply. So over here, our voltage supply is 12 volts. We have to program the circuit to sit at 6 volts, which is midway of the power supply. So over here, instead of the 1K resistor, we have to do a calculation to see what value of resistance will cause the circuit to sit at half of the power supply. So what we seek 6 volts, right? Again, by Ohm's law, 6 volts, voltage is equal to IR again. We know our 6, our I is 8.5, our R is what we seek. So our R is 6 divided by 8.5. What do we arrive at? You arrive at something like 700 ohms, which is not a standard resistor. You are likely to get 680 ohms. But let's get real. We use 1 kilo ohm in our circuit. So let's check what the voltage on collector will be given the true circumstances of the circuit. So we have said that over here we'll have 8.5 volts, right? 8.5 volts as our voltage on the collector resistor. Voltage on collector resistor is 8.5. If so, what will be the voltage on collector? The voltage on collector will be the power supply, which is 12 volts, minus the voltage on collector resistor, VRC. Therefore, our VC is 12 minus 8.5, which leaves us with 3.5 volts. Good. But you notice that this 3.5 volts is not guaranteed because it is loaded by the base emitter junction of transistor T2. To guarantee the 3.5 volts, you have to introduce some emitter resistance here, like we did here, so that the voltage here will be guaranteed. Okay, but again, let's use what we have. So what is going to happen is, over here, the voltage here will be forced to 0.7 volts, whereas the collector voltage on collector will be forced to increase far beyond the mid range. This is not good enough, but it's working. Okay, so let's carry on and determine the input impedance of our amplifier circuit. For this circuit, you notice that as soon as you attach the base current, now the current begins to divide. Some of the current will go here, some of the current will also go here. What it means is that even though the voltage divider was in series, as soon as we attach it to the base, the resistors appear in parallel because of the current division that appear. So the current division causes the input impedance to look like this. RB1 power to RB2 power to ZR. Let's take a moment to define ZR. You will recall that the relationship between the base current and the emitter current is defined by the function beta plus 1. So if you are the base here, this resistance that you see here appears to be multiplied by beta plus 1. So our ZR under this circumstance is RE. But there is also a dynamic resistance which is introduced by the base emitter junction here. Let's call it RE. Since they are all in the emitter lead here, they are both multiplied by beta plus 1. Let's assume that this transistor has a beta of 100, given the collector current at which we are operating the transistor. For RE, we know it. I mean RE1. But for the dynamic resistance, how do we arrive at the value of the dynamic resistance? That is arrived at by a theoretical constant which has been established by scientists from the analysis of the PN junction as this. So they say RE is determined by this constant 26 millivolts divided by the emitter current. Where you don't have the emitter current, you can use a collector current to arrive at a conclusion, granted that the base current is small enough to be ignored. So let's quickly find our RE. Our RE under this circumstance is 2.6 over our emitter current, which is 8.5 milliamperes, which gives us a value of approximately 3 ohms. Because of the small nature of this RE, some engineers will ignore it in order to arrive at their conclusions pretty faster. Okay, so that's our value of RE. Keep that in mind as I clean the board. If that is our RE, then it means our ZR will be equal to 47 plus 3, all multiplied by, we assume a bit of 100, remember? 100 plus 1. This will be 50. So you do the math, it should be a 50 ohms, right? So if you put this in our resistors in power, what it means is that we come to our product over sum. We have R B1 by R B2 by Z R all over R B2 by Z R plus R B1 by Z R plus RB1 by RB2. So you put your values into the formula and you arrive at approximately 3.8 kilo ohms. That is the input impedance of the amplifier that we implemented in part 1 of the video. Now let's see if we can determine the output impedance. The output impedance is simple. You notice that we are driving the speaker directly with the second transistor T2 of the circuit. So what it means is that our output impedance is very, very simple. It will be the 8 ohm speaker impedance. The speaker that we used was 8 ohms. So 8 ohms will be our output impedance. Okay, now let's go to our voltage gain. Our voltage gain, because this is a 2 transistor amplifier, we will establish the voltage gain of the first stage involving T1, AV1. A is for gain. And then the voltage gain of the second stage, and then they will multiply to give us our overall voltage gain. So let's get into it. The voltage gain of the first stage of the common emitter amplifier is like this. Like this, we have RC1 here. You notice that this RC1 is loaded by the base emitter junction of the second transistor T2. So it is in parallel with RE multiplied by beta plus 1. Now, because of the design of the amplifier, there's no emitter resistor here. So it renders the amplifier unpredictable. If there were an emitter resistor here, this voltage here will be guaranteed, and it will lead us to establish easily the voltage in the emitter resistor here. So either we'll break the circuit up, put our multimeter there, or for purposes of simplicity of our analysis, we assume that the current being passed here is 4 milliamperes. If the current being passed here is 4 milliamperes, then it means our small RE here will be, again, we are using this 26 over the emitter current, 26 millivolts over the emitter current, which will leave us with 26 over, we have assumed 4 milliamperes, right? Which leaves us with 6.5 ohms. So if you multiply this 6.5 ohms by the beta, which we have assumed to be 100, it means we have 6.5 ohms by 101. It means this side has become like 650, right? I'm doing these calculations off my head. It will be at 650 our R. Our resistance on the collector, which was 1 kilo ohm, which is 1000, is now in power to 650 something ohms. When you do that with the product over sum rule, what you arrive at is a figure of something like 393. But that is not the voltage gain. The voltage gain is the resistor here divided by the resistor here. So since we have arrived at the top value, the voltage gain, which is this figure, RC power to RE by beta plus 1 all over the resistance in the emitter here, R E plus RE. You do the math, now you arrive at 390, right? 393 divided by 47. The RE for the first stage of the amplifier was 3 ohms, gives us 50. And you do that, your voltage gain for the first stage is determined as 7.86. The voltage gain has no unit. Now let's consider the voltage gain of the succeeding stage built around transistor T2. Now voltage gain for the common emitter amplifier, is determined by resistance in the collector divided by resistance in the emitter. In this circumstance in particular, because there is no emitter resistor there. And from our earlier calculation, we determined that the RE, which is the dynamic resistance for the second stage, was 6.5 ohms. And the speaker impedance under this circumstance is 8 ohms. So 8 divided by 6.5 will give us 1.2. So our overall voltage gain is AV1 by AV2. It gives us, because the first one we arrived at a value of 7.86 for the first stage, and the second one is 1.2. When you multiply, you arrive at 9.43. What it means is that whatever voltage you introduce to the base of the amplifier, and I'm talking about a signal voltage, will be multiplied by a value of 9.43 at the output. This is what the common emitter amplifier circuit is about. We can arrive at the power gain by deducing the current gain, which we shall multiply by the voltage gain. But I'll leave that to you as your homework. If you have any challenge, just hit me up in the comment section and I'll come to your aid. I'll see you around in the next video where we design a more detailed amplifier. In the next video, we shall look at a common emitter amplifier with a common collector output. So here is how the circuit was wired up. I'll see you around.